Imagine you are standing at the center of our galaxy, not visiting, not observing from a safe distance, standing there. Can you feel it, that pull? That invisible, absolute, merciless gravity wrapping around you like a fist made of collapsed space-time. You cannot run, you cannot think, you cannot even scream because sound itself has no future here. Every direction you turn leads to the same destination, down, in. You have just met Sagittarius A, the supermassive black hole sleeping at the heart of the Milky Way, 4 million times the mass of our Sun, compressed into a point so small, so dense, so utterly incomprehensible that the laws of physics, the very rulebook of reality, simply stop working at its edge. Not slow down, not bend, stop. And here is the thing that should keep you awake tonight. This is not the biggest one, not even close, not even remotely close. In fact, compared to the true titans of the cosmos, the objects that sit at the centers of the largest galaxies, presiding over stellar populations of hundreds of billions of stars, governing the fate of everything within reach of their gravity, Sagittarius A is a modest, quiet, almost unremarkable example of its kind, a local specimen, a neighborhood version of something that, in its most extreme incarnations, challenges the very boundary of what physics says is possible. There are black holes in the observable universe so massive that if you replace the word black hole with God of gravity, you would not be speaking metaphorically. You would be speaking physically, accurately, in the only language that does these objects justice. And every single one of them was here long before you were born. Most of them were here long before the Earth existed. Some of them, the oldest, the most enigmatic, the ones that appear in galaxies so ancient their light has been traveling toward us for over 13 billion years, may have been here since the universe was barely learning how to breathe. Before we descend into what supermassive black holes actually are, you need to understand something that most science textbooks will never tell you. Not because the information is classified, not because it is too dangerous for public consumption, but because the full implication of it, the actual meaning of what the data shows, is so unsettling, so cosmologically disorienting, that most presenters quietly sidestep it in favor of safer, more digestible framing. These objects do not simply exist in the universe, they govern it. Every large galaxy we have ever found, every single one, has one buried at its center. Like a dark king seated at the throne of creation, enthroned before the first star of its kingdom had ignited. Science did not predict this. Science discovered it, slowly, reluctantly, over decades of pointed lenses and shattered assumptions. And with every new discovery, every new measurement, every new image, every new detection, the universe revealed a little more of how terrifying the answer truly was. This is not a story about a distant abstract cosmic phenomenon that has no relevance to your life. This is the story of the engine behind everything, the silence at the center of every galaxy, the architects of reality that were never supposed to exist, and yet somehow built everything you have ever seen, every star you have ever named, every constellation you have ever traced, every photon of starlight that has ever touched your eye on a clear night, all of it downstream from them, all of it shaped by their gravity, their feedback, their ancient and ongoing influence on the structure of the cosmos. This is the terrifying truth about supermassive black holes. Before we get started, if you love exploring the depths of space as much as we do, take a second to like this video and subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Act 1. The birth of an impossible idea. Close your eyes and travel back. Not to last year, not to last century, not to the birth of civilization, or the extinction of the dinosaurs, or even the formation of the Earth. Travel back to a time before Earth existed, before the Sun ignited, before the Milky Way had finished assembling its spiral arms. Travel back to approximately 800 million years after the Big Bang, a moment so early in cosmic history that the universe itself was still an infant, still violent, still assembling the first versions of the large-scale structures we would one day map and catalogue and give names to. The universe is still young, still hot, still churning with raw, unprocessed matter collapsing under its own gravity in a billion places simultaneously. The first stars are burning with an intensity that no star alive today can match. Blue-white furnaces consuming fuel at rates that will kill them in millions of years rather than billions. The first galaxies are assembling, their shapes still irregular and unsettled, the process of gravitational collapse still working out the architecture of the cosmos at every scale simultaneously. Now open your eyes. Quasars are burning. Quasars, the most luminous objects in the known universe, are blazing across the early cosmos with a brightness so obscene, so physically transgressive, that a single one of them outshines an entire galaxy of 200 billion stars. Outshines it not by a small factor, not by 2 or 3 times, but by factors of hundreds, sometimes thousands. A single compact region of space, smaller in some cases than our solar system, generating more light than the combined output of every star in the Milky Way. Astronomers first detected them in the 1960s, and they had absolutely no idea what they were looking at. The light coming from these objects was ancient, impossibly ancient. The signals had travelled billions of light years to reach our telescopes, which meant these things were not here anymore. They were there. Relics of an early universe so violent and so energetic that modern cosmology still struggles to fully explain them. The name itself, quasar from quasi-stellar radio source, reflects the original confusion. They looked at first like stars, compact point sources of light, but their spectra were wrong. The wavelengths were stretched by redshift into configurations that implied distances no star could occupy and luminosities no star could produce. What were they? The answer took decades to build, and when it finally arrived, it did not comfort anyone. Quasars are the feeding events of supermassive black holes, the luminous death screams of matter being consumed on a cosmological scale, the radiation produced by the friction and compression of material spiraling inward toward immense horizons at a significant fraction of the speed of light. Not ordinary black holes. Not the stellar remnants left behind when a massive star exhausts its nuclear fuel, collapses under its own gravity, and leaves behind a dense compact object. Those are dangerous enough, certainly. A stellar black hole might contain the compressed mass of 10 to 50 suns, crushed into a sphere perhaps 30 kilometers across. A cannonball of gravity that warps space-time with enough ferocity to trap light and consume anything that wanders too close. Terrifying, certainly, but a rounding error compared to what we are discussing today. Supermassive black holes contain the equivalent mass of millions, sometimes billions, of suns, not compressed into a region the size of a city, like their smaller stellar cousins. Compressed into a region smaller than our solar system, in some cases smaller than the orbit of Neptune, an almost inconceivable density at an almost inconceivable scale, doing something that should not be physically possible, and yet sitting there quietly at the center of almost every galaxy ever observed, as though they have always been there, as though they belong there. They probably do. Here is the paradox that woke cosmologists up at 3 in the morning and refused to let them sleep again. When we look at the earliest galaxies in the observable universe, galaxies that formed only a few 100 million years after the Big Bang, galaxies so distant that their light has been travelling for over 13 billion years to reach our instruments, we find supermassive black holes already there, already enormous, already containing hundreds of millions of solar masses, already mature, already ancient, already presiding over their young galaxies with the settled permanent authority of something that arrived long before everything else. This should be impossible. Standard models of black hole formation require time. A stellar black hole forms when a massive star dies. It then grows by consuming nearby matter, gas, dust, stars, other black holes, in a process that physicists call accretion. Gravity captures matter. Matter spirals inward toward the event horizon. The spiraling generates angular momentum that forms a disk. Friction and compression within the disk heat the infalling material to billions of degrees, generating the blinding radiation we observe as quasar activity. The black hole gains mass. It grows slowly, over billions of years of patient, relentless consumption. Even at the maximum physically permitted accretion rate, a theoretical limit called the Eddington luminosity, beyond which radiation pressure from the heated infalling material pushes outwards so strongly that it halts further accretion. A black hole beginning from a stellar remnant of a few tens of solar masses would require the full current age of the universe, 13.8 billion years, to grow into something containing billions of solar masses. But billions of years had not passed yet. The universe was barely an infant. And yet there were the black holes, enormous, dominant, inexplicable, already sitting at the centers of galaxies that should not have had enough time to build them. Where did they come from? Nobody knows. Not with certainty. Not yet. This is not a gap in public knowledge that the scientists have filled without telling us. This is an open research problem, one of the most actively debated questions in observational cosmology. The formation mechanism of the first supermassive black holes, what cosmologists call the seed black hole problem, remains genuinely, frustratingly, excitingly unresolved, which means we are, right now, in the middle of the story, not at its end, not summarizing conclusions already reached. We are in the part where the mystery is still alive. Several theories have been proposed, each more extraordinary than the last, each with observational evidence to support it and theoretical difficulties to overcome. The first theory suggests that in the earliest universe, before stars had formed at all, enormous clouds of primordial gas, containing the mass of millions of suns, composed almost entirely of hydrogen and helium with none of the heavier elements produced by stellar nucleosynthesis, collapsed directly into black holes without ever passing through a stellar phase. No star formation, no period of nuclear burning, no supernova, just collapse. Pure catastrophic gravitational implosion, going directly from gas cloud to black hole in a transition so extreme it bypassed every intermediate stage. These so-called direct collapse black holes would have formed seeds already containing tens of thousands to perhaps hundreds of thousands of solar masses, large enough to grow rapidly through accretion into the billions of solar masses monsters we observe in the early cosmos, given only a few 100 million years of feeding. The conditions required for direct collapse are specific and delicate. The gas cloud must be massive enough and cool enough to collapse coherently without fragmenting into smaller clumps that would form stars instead of a single black hole. This requires suppression of the molecular hydrogen that would otherwise allow the gas to cool efficiently and break apart. It requires proximity to strong ultraviolet radiation sources, perhaps nearby star-forming regions that destroy the hydrogen molecules before they can cool the cloud into fragmentation. The conditions are restrictive, which means direct collapse black holes would have been rare even in the early universe. But rare is not zero. And rare, given a universe containing trillions of galaxies, means potentially billions of them. The second theory is darker. It focuses on the population 3 stars, the universe's first generation of stars, which have never been directly observed because they burned out and died billions of years before any telescope we currently possess could have seen them, but whose existence is demanded by our models of cosmic chemical evolution. Population 3 stars formed in a universe that contained only hydrogen, helium, and trace lithium. No carbon, no oxygen, no silicon, no iron. None of the elements produced by stellar fusion. This mattered because heavier elements provide additional cooling mechanisms during star formation. In their absence, the gas clouds that formed the first stars could not cool as efficiently, which meant they could not fragment as finely, which meant each fragment was larger, which meant each resulting star was larger, potentially enormously larger. Theoretical models predict population 3 stars might have contained hundreds, or even thousands of solar masses. Stars so massive they would have burned through their fuel in millions of years rather than billions, exploding as hypernovae or collapsing directly into black holes without an explosion at all, leaving behind remnants of thousands or tens of thousands of solar masses, already head-started on the growth towards supermassive scales. These titanic first stars have never been directly observed. They are ghosts in the cosmic record, inferred from the chemistry of everything that came after them. But the James Webb Space Telescope is now probing redshifts high enough that the detection of population 3 stars, or at least their signatures in the spectra of very early galaxies, may be within reach. We are potentially only years away from seeing the ancestors of the first black holes. A third theory is perhaps the most unsettling of all, because it does not require any stellar or gas physics at all. It proposes that some of the black holes we observe today were formed not after the Big Bang, but during it. Primordial black holes, born in the chaos of the universe's first fractions of a second, woven into the fabric of space-time before the first atom had finished forming, before nucleosynthesis had begun, before the universe had cooled enough for matter and radiation to decouple. In the earliest moments after the Big Bang, quantum fluctuations in the density of the universe were amplified by inflation, the hypothetical period of exponential expansion that cosmologists believe preceded the hot dense phase we call the Big Bang itself. Most of these density fluctuations were small enough that they dissipated harmlessly as the universe expanded. But if some regions of the primordial plasma had density contrasts large enough, they would have collapsed under their own gravity before the universe had expanded enough to prevent it, forming black holes that predated everything, every star, every galaxy, every atom of the periodic table. Primordial black holes could range enormously in mass, depending on when during the early universe they formed. And if some of them had masses in the range of millions of solar masses, if the density fluctuations that seeded them were large enough, then they would have been ready-made seeds for the supermassive black holes we observe, requiring no stellar precursors, no accretion from scratch, no growth phase to explain. 3 theories, each extraordinary, each with evidence, none yet definitive, none yet proven, each representing a different answer to the same question. How did the universe produce, in its very infancy, the engines that would go on to govern its entire future history? But all of them arrive at the same terrifying conclusion. Supermassive black holes did not arrive late to the story of the universe. They may have been here from the beginning, and everything that came after, every star, every planet, every galaxy, every atom of every living thing that has ever drawn breath, came after them and was shaped by them and exists in the spaces they left between their influence. We did not inherit a universe, we inherited their leftovers. Act 2. The anatomy of an absolute nightmare. Let us now descend. Let us go toward one of them and understand. with the clarity that only proximity can provide, with the specific, bone-deep understanding that only comes from approaching something dangerous, exactly what we are dealing with. Start at a distance of 1 light-year from the center of a supermassive black hole. Let us use Sagittarius A as our guide, our own galaxy's central monster, the nearest supermassive black hole, the one whose gravitational influence is closest to your own life, even if its distance makes that influence negligible at the scale of solar systems. At 1 light-year from its center, you would notice nothing extraordinary. Space looks normal. Stars are visible in the distance. The gravitational pull, while stronger than empty interstellar space, is not dramatically different from many other regions of the galaxy. There is no obvious sign that you are approaching the most extreme gravitational environment in the Milky Way. You would have no indication, from local measurement alone, of what lies ahead. This is the first dangerous thing about black holes. They do not announce themselves. Move closer. 100 astronomical units out, roughly the distance from the Sun to the very edge of our solar system's Oort cloud, the vast spherical shell of cometary bodies that marks the outer boundary of the Sun's gravitational dominance. Now things begin to change. The distribution of stars around you grows denser. Older, faster-moving stars occupy this region, their velocities elevated by the gravitational influence of the compact mass ahead. The gravitational gradient, the rate at which gravity strengthens as you move inward, becomes more pronounced. You are beginning to feel the asymmetry, not with your body, but with instruments. The pull is not yet fatal, not yet absolute, but it is present and it is patient. Move closer still, 10 astronomical units, the distance from the Sun to Saturn. Now the stars around you are moving differently. They are orbiting, not slowly, the way Earth orbits the Sun in a leisurely journey measured in years, at a stately 30 kilometers per second. These stars are racing, screaming around the black hole at thousands of kilometers per second, their paths bent and distorted by a gravity so intense it does not merely pull them. It manipulates the very geometry of the space they travel through. This is not metaphor. This is not poetic license taken with a complex physical concept. General relativity tells us, and observations confirm with exquisite precision, that mass curves spacetime itself. A sufficiently massive object does not pull other objects toward it through some invisible force acting across empty space, the way Newton imagined. It warps the fabric of the space those objects travel through, causing them to follow curved paths that lead, inevitably, inward. Near a supermassive black hole, this warping is total. The landscape of spacetime has been demolished and rebuilt in the shape of an inescapable funnel. Now you reach the boundary that separates comprehension from impossibility, the event horizon. It does not look like anything. There is no wall, no visible surface, no wall of fire, no dramatic visual cue distinguishing the inside from the outside. The event horizon is simply a mathematical threshold, a sphere of no return defined by a quantity called the Schwarzschild radius, named after Karl Schwarzschild, who derived its value from Einstein's equations of general relativity in 1916, while serving in the German army during World War I. In the trenches of the Eastern Front, under artillery fire, between battles, he found the first exact solution to Einstein's field equations, a feat that Einstein himself had thought would require approximations and might take years, and mailed his calculations to Einstein, who read them in disbelief. Not because they were wrong, because they were right. Because what they predicted was so extreme, so geometrically catastrophic, so physically final, that Einstein himself was not certain nature would permit it. Nature, as it turned out, not only permitted it, nature preferred it. The Schwarzschild radius defines the point at which the escape velocity, the speed required to break free from the gravitational pull of the central mass, reaches the speed of light. Cross it from the outside moving inward and nothing returns. Not matter, not energy, not information, not light itself, not time in any form that connects to the universe outside. The interior of a black hole is not merely a region of extreme gravity, the way the deep interior of a star is a region of extreme pressure and temperature. It is, in the most literal physical sense, a different place, a region of spacetime that is causally disconnected from our universe. A room with no door, no window, no way out, not because the walls are strong, but because the geometry of spacetime inside has been bent into a configuration where all paths lead inward. You cannot escape, not because you lack sufficient thrust, not because your technology is insufficient, but because there is no direction called away anymore. All directions, past the event horizon, lead to the same destination, the singularity now. This is the point where the equations break, where the most successful theory in the history of science reaches into the darkness ahead and produces an answer that cannot be real. A singularity is what general relativity predicts exists at the center of a black hole, a point of infinite density, infinite space-time curvature, a location where the mass of millions or billions of suns has been compressed to a mathematical point of zero volume. The mathematics of general relativity, applied honestly and without fudging, produce infinities at the singularity. And infinities in physics are not answers, they are distress signals. They are the equation's way of waving a white flag and admitting that something fundamental is missing from our understanding, that we have pushed a theory beyond the domain of its validity, into territory where a better, more complete theory is needed but does not yet exist. We do not know what actually exists at the centre of a black hole. We know what our best theory predicts. We know the prediction cannot be physically real as stated. And we know we do not have the better theory yet. This is not a temporary gap that will be filled in next year's physics journal. The reconciliation of general relativity and quantum mechanics, a theory of quantum gravity capable of describing the singularity's true nature, is the central unsolved problem of theoretical physics. It has been worked on continuously by the smartest minds alive for over a century. It has not been solved. Not in the way Maxwell solved electromagnetism. Not in the way Einstein solved gravity. The singularity remains, as it has always been, a locked door at the centre of a black hole and a locked door at the centre of physics. The singularity is the universe's way of telling us that we are not finished yet. For the supermassive black hole at the centre of the Milky Way, Sagittarius A, with its 4 million solar masses, the event horizon has a radius of approximately 12 million kilometres. The Sun's radius is about 700,000 kilometres. The event horizon of Sagittarius A is roughly 17 times as the size of the Sun, a sphere 24 million kilometres in diameter, sitting at the centre of our galaxy, inside of which the laws of physics as we understand them cease to operate. Sit with that number for a moment, 24 million kilometres in diameter. A sphere you could not cross in a spacecraft travelling at the speed of sound in one lifetime. Entirely contained within a volume that the Milky Way's 400 billion stars orbit without noticing, most of them never approaching closer than thousands of light years. And yet it controls the trajectory of every star in the galaxies through the long-range grip of its gravity. Now consider TON 618. TON 618 is a quasar located approximately 10.4 billion light-years from Earth, in the constellation Canes Venatici. The light reaching our telescopes from TON 618 departed when the universe was approximately 3.4 billion years old, less than a quarter of its current age. It contains a black hole with a mass of 66 billion solar masses, 66 billion. Not 66 million, not 6 billion, 66 billion suns compressed into a region of space. Its event horizon has a radius of approximately 1300 astronomical units. For reference, 1 astronomical unit is the distance from Earth to the Sun, approximately 150 million kilometers. The entire solar system, everything from the Sun to the very edge of the Kuiper belt, the belt of icy objects beyond Neptune's orbit that includes Pluto, spans roughly 50 astronomical units. TON 618's event horizon is approximately 26 times larger than our entire solar system. If TON 618 were placed at the centre of our solar system, if Sagittarius A were swapped out for TON 618, and we somehow survived the transition long enough to measure what had changed, the event horizon would extend far beyond the orbit of Neptune, past the Kuiper belt, into the inner Oort cloud. Every planet you have ever been taught the name of, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, would be inside the event horizon. Every moon of every planet, every asteroid in the asteroid belt, every comet on its long elliptical journey through the outer solar system, all of it inside a sphere of no return from which nothing and no one would ever escape. Pluto would be inside it. The entire planetary family of the Sun, every world, every moon, every rock, every grain of ice we have ever mapped, would be consumed before you reach the edge of the point of no return. Sit with that, not for a moment, sit with it until it becomes real. Until the numbers stop being numbers and start being actual space, actual distances you can picture, actual volumes you understand from living inside the solar system your whole life. There is an object in the observable universe, one of at least several that large, whose event horizon alone is 26 solar systems wide, and we have never seen what is inside it. We have never seen what is inside any of them. All we have is the mathematics of what happens at the boundary, and the silence from beyond it. Act 3. The feeding nothing about a supermassive black hole is passive. This must be made absolutely clear, because the popular image of a black hole, a dark static void sitting inertly in the cosmos like a drain in the floor of the universe, is not just incomplete. It is catastrophically wrong. Supermassive black holes are engines. They are the most efficient energy conversion machines in the known universe. When they feed, they do not merely consume. They transform, and in transforming, they release energy at scales that defy every other energetic process in astrophysics. The nuclear fusion reactions that power every star that has ever burned in every galaxy that has ever existed are, by comparison, inefficient. A hydrogen bomb converts less than 1% of its mass to energy. Stellar nuclear fusion converts approximately 0.7% of hydrogen mass to energy. An actively accreting supermassive black hole, converting the kinetic and thermal energy of infalling matter into radiation through the physical processes of the accretion disk, can convert up to 42% of the rest mass energy of infalling matter into radiation. 42%, 60 times more efficient than nuclear fusion. The most energetically efficient process occurring naturally in the observable universe. When a supermassive black hole feeds, it becomes the most violent machine that physics permits. The feeding process begins at a distance. Matter, gas clouds stirred up by gravitational perturbations, the molecular material of disrupted nebulae, the stellar debris of stars torn apart by tidal forces, even the gas shed by normal stellar winds in the crowded galactic center, begins to fall inward under gravitational attraction. But matter falling into a black hole does not fall straight in, the way water falls straight down from a tap. Angular momentum, the same physical property that causes a spinning figure skater to speed up when she pulls her arms in toward her body, causes the infalling material to spiral. The matter has some initial rotation, some component of velocity perpendicular to the radial direction, and as it falls inward and accelerates, conservation of angular momentum causes that perpendicular velocity to increase. The infall becomes a spiral. The spiral, collecting material from all directions, flattens into a disk. A vast, swirling, superheated structure of plasma extending for light years in some cases, orbiting the black hole at a significant fraction of the speed of light. This is the accretion disk, and it is one of the most energetic, most extreme, and most physically rich environments in the entire universe. The physics of what happens inside the accretion disk is extraordinary and violent. As matter spirals inward through the disk, conservation of angular momentum causes its orbital velocity to increase. The innermost regions of the disk, just outside the event horizon, are moving at a substantial fraction of the speed of light. The interaction between adjacent layers of the disk moving at different velocities generates friction, an enormous, continuous billion-degree friction. But ordinary viscosity is insufficient to transport angular momentum outward through the disk fast enough to allow accretion to proceed at the observed rates. The real mechanism is magnetic, the magnetorotational instability, a process in which the differential rotation of the disk amplifies tangled magnetic field lines, generating turbulence that efficiently transports angular momentum outward and allows matter to spiral inward toward the event horizon. This magnetically turbulent, plasma-hot environment reaches temperatures of billions of degrees in the innermost regions, temperatures that exceed the surface temperature of the Sun by factors of thousands. At these temperatures, the material radiates not merely invisible light but across the entire electromagnetic spectrum simultaneously. Radio waves, infrared, visible light, ultraviolet, X-rays and gamma rays, all pouring outward from the disk at luminosities that can exceed the combined output of every star in an entire galaxy of 100 billion suns. One object, smaller in extent than the solar system, outshining 100 billion stars. This is a quasar. This is what happens when a supermassive black hole feeds actively. This is the most luminous sustained phenomenon in the known universe, powered by the most efficient energy conversion process that physics permits, fed by the most extreme gravitational field that exists. But the accretion disk is only the beginning, because the feeding produces a secondary phenomenon that is in some ways even more consequential than the disk itself. The magnetic fields generated in the maelstrom of the accretion disk become extraordinarily powerful, threaded through the hot plasma, tangled and amplified by the magnetorotational instability, concentrated and focused by the geometry of the disk and the black hole's rotation. At the poles of a spinning black hole, a region of extreme frame dragging where the rotation of the black hole itself twists the surrounding space-time, these magnetic fields become organized into two narrow, extraordinarily focused channels. And through these channels, a fraction of the infalling material, rather than crossing the event horizon, is instead flung outward, accelerated by the combined magnetic, rotational and gravitational forces of the system to velocities approaching the speed of light, collimated into jets so narrow they extend for millions of light years without dispersing. Relativistic jets. Columns of plasma and high-energy particles moving at 99.9% of the speed of light, erupting from the poles of a feeding supermassive black hole, penetrating through the host galaxy, through the gas surrounding the galaxy, through the intergalactic medium of the galaxy cluster, carving cavities in the hot plasma of cosmic structures containing the mass of millions of galaxies. Two lances of gamma-ray energy, extending outward for distances measured in millions of light years, powered by a process occurring in a region smaller than our solar system. These jets are audible in a sense that most people find deeply unsettling when they first learn of it. Not directly, not in the way that sound travels through air, but through the pressure waves they drive through the hot plasma of galaxy clusters. In 2003, NASA's Chandra X-ray Observatory, imaging the Perseus galaxy cluster approximately 240 million light-years away, detected ripples in the X-ray emission of the hot intracluster gas. Concentric rings of slightly higher and lower density propagating outward from the central region, from the supermassive black hole at the center of the galaxy NGC 1275, which sits at the cluster's core. Real pressure waves, real acoustic oscillations propagating through the plasma. Sound waves, in the most technically accurate sense of the term, generated by the periodic activity of the jets. Each burst of jet power driving a pressure wave outward into the surrounding medium, creating a pattern of concentric rings visible in X-rays, audible in principle if scaled to frequencies accessible to human hearing. Scientists did scale them. They converted the frequency of these pressure waves, cycling once every 10 million years, up by 57 octaves, spanning more than 50 octaves beyond the highest note a piano can produce, into the range of human hearing. And the result was a single sustained note, a B-flat, the lowest B-flat ever measured anywhere, 1 million billion times lower in frequency than the lowest note detectable by the unaided human ear. A note so low that its individual cycles last 10 million years. The black hole at the center of the Perseus clusters has been sustaining that note for over 1 billion years. It is not done singing. There is a specific event that occurs when a star wanders too close to a supermassive black hole, not across the event horizon, but within the tidal radius, the distance at which the difference in gravitational pull across the diameter of the star exceeds the star's own self-gravity. Within this radius, the star cannot hold itself together. Its near side is pulled more strongly toward the black hole than its far side. The differential force, the tidal force, exceeds the gravitational binding energy of the star itself. And in a process with a name as clinical as it is horrifying, the star is disrupted. A tidal disruption event. The star is not swallowed whole. It is spaghettified, and while that term carries an almost absurd lightness, it should be understood that the reality it describes is not light in any sense. The star is stretched along the radial direction by differential gravity, the near side accelerating faster than the far side, and simultaneously compressed in the perpendicular directions. It is elongated into a long, thin stream of stellar material, a thread of plasma containing an entire solar system's worth of mass, wrapping around the black hole and forming a debris stream that eventually circularizes into a new accretion disk. Half the debris is accreted by the black hole. Half is ejected back outward in a flare of radiation that can briefly, for weeks or months, outshine the entire host galaxy. The optical signature of an entire sun being destroyed. The funeral pyre of a star, visible across hundreds of millions of light-years of intergalactic space. We have observed these events. We have watched stars die this way in real time. Their last light arriving at our telescopes after journeys of millions or hundreds of millions of light-years. In 2019, an event designated AT219 Quiz was detected, a tidal disruption event caught early enough in its development that astronomers could observe the star unraveling in real time, watching the flare build from its first stages, tracking the radiation as the debris circularized and fell inward, watching a star older than Earth's own sun be consumed in a process lasting only months. It took approximately 215 million years for the light of that event to reach us. The star was gone long before the first dinosaur walked on Earth. We watched it die in 2019. Act 4. The architecture of terror here is the part that the standard popular science presentation tends to skip. Not because it is too technical, not because it requires advanced mathematics to understand, but because its implications are uncomfortable in a way that goes beyond the visceral horror of event horizons and tidal disruption events. Because it reframes the universe you live in from a place where black holes are extreme but peripheral, exotic objects at the centers of distant galaxies, impressive but irrelevant to your daily existence, into something far more unsettling. It is not just the extreme local physics of black holes that should fill you with a specific, cold variety of dread. It is their role, their absolutely foundational, inescapable structural role, in the architecture of everything. Every large galaxy has one. Not most, not the majority. The Milky Way has Sagittarius A. Andromeda, our nearest major galactic neighbor 2.5 million light-years away, a galaxy broadly similar to our own, has a supermassive black hole estimated at 100 million solar masses, 25 times more massive than Sagittarius A. The giant elliptical galaxy Messier 87, approximately 55 million light-years away in the Virgo cluster, has a black hole of 6.5 billion solar masses, 1,600 times more massive than the one at the center of our own galaxy. M87, the black hole at the center of Messier 87, became on April 10, 2019, the first black hole ever directly imaged. The Event Horizon Telescope collaboration, a network of radio telescopes distributed across the globe, combined using very long baseline interferometry to create an effective telescope the size of the Earth, released an image that had taken years of observation, hundreds of edits of data, and the combined analytical effort of hundreds of scientists to produce an orange-gold ring of light, a blurry asymmetric annulus glowing against the darkness. Inside it a region of shadow, the shadow of the event horizon, the boundary of no return, rendered visible for the first time in human history. The image looked like something you might see on a coin, or on an ancient astronomical diagram. Simple, almost diagrammatic in its clarity despite the blur of limited resolution. And yet what it represented, the audacity of what it actually was, is still not fully appreciated by everyone who saw it. Humanity had taken a photograph of the edge of physics, a portrait of the place where our equations end. We had built an instrument the size of a planet, and pointed it at an object so far away its angular size on our sky was approximately the same as a golf ball on the surface of the moon, and we had resolved it. We had seen it, not inferred it, not detected it indirectly, seen it. The relationship between supermassive black holes and their host galaxies is not incidental, not accidental, not a coincidence of spatial proximity. The black hole happened to form near the center of the galaxy, and here they both are. The relationship is structural, causal, active, and it runs in both directions simultaneously. The black hole regulates the galaxy. When a supermassive black hole feeds actively, when sufficient matter falls within its gravitational reach to trigger a period of enhanced accretion and jet activity, the energy it releases into the surrounding environment is staggering. The jets, the radiation, the winds of particles driven outward at relativistic speeds by the pressure of the accretion disk. All of this energy interacts with the gas reservoirs of the host galaxy. It heats the gas, it disperses it. It creates pressure waves that propagate through the interstellar medium. It drives bulk outflows of gas out of the galaxy altogether. And most consequentially, it prevents the gas from cooling and condensing into the dense clouds that would otherwise collapse under their own gravity to form new stars. A sufficiently powerful period of quasar activity can effectively shut down star formation across an entire galaxy, sterilizing thousands of light-years of space in all directions, preventing the birth of hundreds of billions of potential suns, turning a galaxy that would otherwise continue producing new stars into a red and dead system, a population of aging stars gradually dimming over billions of years, with no new generation being born to replace them. This process, called AGN feedback, where AGN stands for active galactic nucleus, is now understood to be one of the primary mechanisms controlling how galaxies evolve over cosmic time. Without it, our models of galaxy formation produce too many large bright galaxies, too many stars, too much stellar mass. The universe in simulations without AGN feedback looks dramatically wrong compared to the universe we actually observe. With AGN feedback included, the simulations produce galaxy populations that match observations across cosmic time. The black hole is not just living at the center of the galaxy. The black hole is managing the galaxy, regulating its star formation rate, controlling its growth, shutting down its stellar nurseries when conditions become too productive, and allowing them to restart when the black hole quiets and its feedback weakens. The mass of a galaxy's central black hole correlates tightly with the mass of its stellar bulge, the central, roughly spherical component of the galaxy's stellar population. Not approximately, across all galaxy types, across all cosmic epochs. A galaxy with a massive bulge has a massive black hole. A galaxy with a modest bulge has a modest black hole. The ratio is consistent, universal, and precise in a way that implies not coincidence but deep co-evolutionary entanglement. The two grew together, regulated each other, shaped each other's development across billions of years, through a feedback loop that operated across thousands of light-years of space between the central engine and the distant star-forming regions. Remove the black hole from a galaxy's history, and you would not recognize the galaxy it became. The Milky Way without its central black hole evolved over 13 billion years, would be a completely different structure, more stars, different spatial distribution, different chemical enrichment history, different orbital dynamics. The spiral arms you see when you look at galaxy images would be shaped differently. The stellar mass budget would be different. We live inside the legacy of a black hole's architecture. Everything you have ever seen, every photon of starlight that has ever crossed your path, every element in your body forged in the cores of stars, all of it exists in a galaxy that was shaped, over billions of years, by the activity of the 4 million solar mass object sitting 26,000 light-years away from you right now. You are the accidental product of a black hole's feedback. Everything you are is downstream of its influence. Now consider what happens next, not in the distant abstract future of cosmological timescales, in the relatively near future by cosmic standards. Sagittarius A is currently quiet, dormant. a sleeping giant rather than a roaring engine. Its last significant feeding event, a period of substantial accretion activity that astronomers believe occurred several million years ago, produced what we now call the Fermi bubbles, two enormous lobes of high-energy gas extending approximately 25,000 light-years above and below the galactic plane, first detected by the Fermi Gamma-ray Space Telescope in 2010. Ghost signatures of a feeding event so energetic it left permanent marks on the structure of the entire galaxy. Since then, Sagittarius A has been absorbing relatively little. It glows faintly in radio and X-ray wavelengths, occasionally flaring briefly when a gas cloud or stellar debris crosses its accretion region, but nothing like the continuous blazing luminosity of an active quasar. It is waiting, in the patient way that only something with no biological clock can wait, and it has been witnessed, in 2019, beginning to consume the remains of a gas cloud called G2 that had passed close enough to be partially disrupted. A small feeding event, a reminder that the quiet is not permanent, but the Milky Way and the Andromeda Galaxy are on a collision course. This is not speculation. It is a measured fact, confirmed by proper motion measurements from the Hubble Space Telescope and Gaia satellite. In approximately 4.5 billion years, the two galaxies will begin to merge, a process that will not be violent in the way a car crash is violent, since galaxies are mostly empty space and individual stars almost never collide directly, but which will be catastrophic in the sense that it will completely restructure both galaxies over hundreds of millions of years. Stars will be flung onto new orbits. Gas clouds will be compressed and triggered into bursts of star formation. The spiral structures of both galaxies will be disrupted and rebuilt into a new, probably elliptical merged galaxy, sometimes called Milkomeda in speculative cosmology, a name that carries more whimsy than the reality it describes deserves. And most relevantly, the merger will funnel enormous quantities of gas and stellar debris toward the central regions of both galaxies, toward Sagittarius A, toward Andromeda's central black hole, toward both of them simultaneously, as the galactic cores approach each other on their long orbital dance toward merger. When that happens, Sagittarius A will wake up. The increase in available matter will trigger renewed accretion activity. The Milky Way's quiet heart will become, once again, an active galactic nucleus, perhaps not a full quasar-level event, but a period of elevated feeding and jet activity that will light up the galactic center and reshape the gas environment of the merger remnant. The Fermi bubbles, already testimony to past activity, will be joined by new structures, new jets, new cavities, new X-ray signatures of feedback energy deposited into the surrounding medium. And eventually, on timescales of billions of years after the galaxy merger begins, the two black holes themselves will find each other. Sagittarius A and Andromeda's central monster, each the inheritor of a galaxy's worth of gravitational history, will spiral toward each other through the dynamical friction of the stellar populations around them. They will form a binary system. Two black holes orbiting each other, their mutual gravity generating gravitational waves that carry energy away from the system, causing their orbit to decay. Slowly, over millions of years, spiraling inward, the gravitational wave emission increasing as the separation decreases, building toward the moment of merger, a catastrophic coalescence producing a gravitational wave burst detectable across the observable universe, and leaving behind a single merged black hole presiding over the galaxy that results. This is the future of the Milky Way, this is what is coming, and the sun will still be burning when it begins. Act 5. Things that should not be. We have been discussing black holes as though our understanding of them is essentially complete, as though the remaining questions are edge cases, footnotes, technical details to be resolved by the next generation of astronomers. This is not accurate. The remaining questions are not at the edges of our understanding. The most important remaining questions are at the center of it. In 1974, Stephen Hawking published a calculation that changed everything, not in the way physics papers usually change things, by extending and refining an existing framework, but in the way that reveals the existing framework is internally inconsistent at a level that demands a fundamental revolution in understanding. Working at the difficult and poorly charted intersection of quantum mechanics and general relativity, two theories that are individually the most precisely confirmed in the history of science, but which, when applied simultaneously to the same problem, produce contradictions. Hawking demonstrated that black holes are not perfectly black. They emit radiation. Not from inside the event horizon, nothing escapes from inside the event horizon, but from the boundary itself. The quantum vacuum, the state of lowest energy in quantum field theory, which is not actually empty but filled with virtual particle pairs continuously appearing and annihilating, behaves differently near the event horizons than it does in flat spacetime. Near the horizon, the extreme spacetime curvature separates virtual pairs before they can annihilate. One particle falls inward past the event horizon, the other escapes outward. The escaping particle is real. It carries positive energy away from the black hole, while the infalling particle carries negative energy, effectively reducing the black hole's mass. Over time, as more and more energy escapes in the form of this Hawking radiation, the black hole loses mass and shrinks. It evaporates. For a stellar black hole, the evaporation timescale is already fantastically long, far longer than the current age of the universe. Hawking radiation from stellar black holes is so cold and so faint that it is currently undetectable by any instrument we possess. But for a supermassive black hole, the evaporation timescale stretches to 10 to the power of 100 years, a googol of years. That number is so large that every comparison available to communicate it falls short. The universe is 13.8 billion years old, approximately 10 to the power of 10 years. The evaporation timescale of a supermassive black hole exceeds the age of the universe by approximately the same multiplicative factor as the age of the universe exceeds 1 nanosecond. It is not a finite number in any human sense. It is a number that exists as pure mathematics, untethered to anything experiential. It is simply forever. But Hawking's calculation produced a problem that has festered, unresolved for more than 50 years. A problem that John Preskill, one of the world's leading quantum information theorists and a former opponent of Hawking's in a famous scientific bet, has described as the most pressing problem in theoretical physics. A problem that does not just challenge one theory or require one extension. A problem that puts the two greatest theoretical frameworks in scientific history in direct, apparently irreconcilable conflict. The information paradox. Quantum mechanics contains, at its absolute foundation, a principle called unitarity, the conservation of quantum information. Every quantum state evolves forward in time according to a deterministic equation, the Schrödinger equation, that is perfectly reversible. Information is never created from nothing. And, crucially, fundamentally, with no exceptions permitted by the theory, information is never destroyed. The quantum state of the universe today is the complete and reversible forward evolution of the quantum state of the universe yesterday. Given perfect knowledge of the present quantum state, you could run the equations backward and reconstruct the complete past. The universe keeps perfect records. Quantum mechanics demands it. Black holes appear to violate this principle absolutely. Matter falls in. Information about the matter, its complete quantum Heysen state, every detail of its physical history, the wave function that fully describes it, falls in with it. The black hole's external properties provide no information about what fell in. According to the no-hair theorem, a classical black hole is entirely characterized by just three quantities: its mass, its electric charge, and its angular momentum. Everything else, the composition, the quantum state, the history of every particle that ever crossed the event horizon, is invisible from outside. And when the black hole eventually evaporates through Hawking radiation, the radiation produced appears to be purely thermal. Random, featureless, the quantum equivalent of white noise, carrying no information about what fell in. Identical whether the black hole formed from a collapsing star, or from an equivalent mass of old novels, or from a collection of antimatter, or from anything else at all. All the information, the quantum state of every star, every planet, every photon, every elementary particle that crossed the event horizon over billions of years of feeding, appears to simply vanish when the black hole evaporates. Quantum mechanics says this cannot happen. Information cannot be destroyed. Unitarity is not a preference, it is a requirement of the theory. General relativity says it does happen. The event horizon seals information away. The singularity terminates the world lines of infalling matter. Nothing returns. Both theories are correct in every domain where they can be tested without reference to black hole evaporation. The most precisely tested theories in scientific history, and they flatly contradict each other. Something is wrong. Something fundamental is missing. 3 candidate resolutions have been proposed, each with serious adherents and serious problems. The first, favoured by most quantum information theorists, including Hawking himself in his later years, is that the information is somehow encoded in the Hawking radiation, subtly and cryptically, in correlations between individual emitted quanta that render the radiation not truly thermal, but only apparently so. This would preserve unitarity. The information would not be destroyed, but would be spread across the outgoing radiation in an impossibly complex, practically unreadable encoding. The problem: the mechanism by which this encoding would occur requires new physics beyond standard quantum field theory. The specific way in which information would escape the event horizon, the process by which the quantum state of infalling matter would imprint itself on the outgoing radiation, is unknown. It cannot be explained within current theoretical frameworks without invoking additional structures. The most prominent current proposal involves islands of space-time inside the black hole that become quantum entangled with the exterior in a way that allows information to eventually be recovered, a framework called the page curve calculation, which produces the right answer for when information should start escaping but leaves the detailed mechanism obscure. The second resolution, that a small remnant survives the final stages of evaporation, a Planck-scale object encoding all the information of everything that ever fell in, requires an object of near-zero mass to store an arbitrarily large amount of information. This violates entropy bounds and creates problems with the effective field theory description of low-energy physics that are arguably worse than the problem the remnant is meant to solve. The third firewall theory, proposed by Ahmed Al-Mahiri, Donald Marolf, Joseph Polchinski, and James Sully in 2012, known by the acronym AMPS, is perhaps the most aggressive. It argues that the event horizon cannot be smooth and featureless, that the requirement of unitarity, combined with the quantum entanglement structure of Hawking radiation, demands that the event horizon be a wall of high-energy quanta, a literal firewall, that would incinerate anything attempting to cross it. The infalling observer does not have a smooth, uneventful horizon crossing. They are destroyed at the horizon. But the firewall requires violating either the equivalence principle of general relativity, the principle that a freely falling observer in a gravitational field is locally equivalent to an observer in free space, or the monogamy of quantum entanglement, a fundamental property of quantum mechanics. Either violation would break a pillar of established physics. There is no clean answer. The smartest people alive have spent careers working on this problem. They have published thousands of papers, constructed new mathematical frameworks, proposed exotic mechanisms from black hole complementarity to holographic descriptions to wormhole connections between the interior and exterior. The information paradox remains open, not almost resolved, not awaiting only technical details. Open as a fundamental wound in the body of physics, bleeding into every attempt to build a unified theory of everything. A black hole is not just an extreme astrophysical object. It is a philosophical crisis wearing the costume of an astronomical one. Act 6. Monsters among monsters. If what we have covered so far has not unsettled you, if the event horizons and the singularities and the information paradox and the feeding and the jets have been absorbed without leaving a lasting disturbance, then permit one final escalation before we step back to the larger picture. Consider Phoenix A, located approximately 5.8 billion light-years from Earth. At the center of the Phoenix galaxy cluster, one of the most massive galaxy clusters in the known universe, sits what is currently believed to be the most massive black hole ever directly measured. Phoenix A, the central engine of the brightest cluster galaxy in this system, has been estimated at approximately 100 billion solar masses. 100 billion solar masses, not 100 million, not 100 billion combined across multiple objects. One single black hole, 100 billion times the mass of the Sun, compressed into a region of space that is still, despite its incomprehensible mass, smaller in linear extent than the distance light travels in a year. Its event horizon has a radius of roughly 590 billion kilometers, approximately 4,000 astronomical units. This is not 26 solar systems wide like TON 618's event horizon. This is 80 solar systems wide. An event horizon extending 4,000 times the distance from Earth to the Sun, in every direction simultaneously. And Phoenix A is so massive that standard theoretical models for black hole growth struggle to explain its existence. Maximum efficiency accretion. Accretion at the Eddington limit, the highest physically permitted rate, applied to a realistic seed black hole over the full age of the universe, does not comfortably produce 100 billion solar masses. Phoenix A sits at the edge of what standard models predict should be possible, and potentially beyond it. Some researchers have speculated that Phoenix A grew through repeated mergers smaller supermassive black holes as the galaxy cluster itself assembled through hierarchical merging, a process in which galaxy clusters grow by cannibalizing smaller galaxy groups, bringing their central black holes along and eventually merging them. But even this does not fully resolve the tension. Phoenix A may require new physics. And if Phoenix A pushes the models, consider what theory predicts might exist but has not yet been found. Physicists have proposed a class of objects called ultramassive black holes. Black holes exceeding 10 billion solar masses as a distinct category beyond the standard supermassive. Phoenix A qualifies comfortably, but theoretical models of hierarchical merger histories in the most extreme galaxy clusters have suggested the possible existence of black holes approaching 1 trillion solar masses. Objects that would contain the equivalent mass of entire small galaxy clusters, with event horizons hundreds of solar systems wide, presiding over structures at the very apex of the cosmic hierarchy. We have not found one yet. We are not certain they cannot exist. and the James Webb Space Telescope is still looking. There is a deeper category of strangeness still, and it has a different flavour from everything else we have discussed. Not the strangeness of extreme physics at known scales, but the strangeness of the unknown, the specific intellectual vertigo of realizing that our best model of the universe may be fundamentally incomplete in a way we are only now beginning to measure. In 2022, 2023, and 2024, data from the James Webb Space Telescope began arriving in quantities sufficient to challenge something that cosmologists had considered one of the most robustly tested frameworks in all of science. Webb found galaxies that should not exist, not marginally unusual galaxies, not slightly surprising galaxies. Galaxies described, in peer-reviewed publications, as impossible, massive, structured, chemically evolved galaxies containing hundreds of billions of solar masses worth of stars, exhibiting the organized morphologies and stellar population properties of systems that had been forming stars for billions of years, detected at redshifts corresponding to the universe being less than 700 million years old. In some cases less than 500 million years old, less than 4% of the universe's current age. Our standard cosmological model, the lambda-cold dark matter model, the most precisely constrained and repeatedly verified description of cosmic structure formation ever developed, predicts that galaxies this massive and this evolved simply cannot exist that early. The timeline of hierarchical structure formation, in which small clumps form first and larger structures assemble through mergers over billions of years, does not permit it. The galaxies Webb is finding are not slightly ahead of schedule. They are impossibly, catastrophically ahead of schedule, and at the centres of at least some of them, detectable through the luminosity signatures of their nuclear regions, are supermassive black holes already enormous beyond any explanation our models offer. Already billions of solar masses, already active, already feeding, already shaped by episodes of GN feedback, already finished with growth phases that our models say should have taken far longer than the universe had been alive. This is not a 10% discrepancy that calibration adjustments might resolve. This is the observations disagreeing with the best tested model in cosmology by factors of orders of magnitude in some cases. Something fundamental about the physics of the early universe, perhaps the nature of dark matter, perhaps the initial power spectrum of density fluctuations, perhaps a new mode of star formation or black hole growth that has no analogue in the present universe, may be wrong in our textbooks. The James Webb Space Telescope was designed to answer questions about the early universe. What it is doing instead is revealing that our questions were not complete enough. The answers we thought we had were answers to the wrong questions. Act 7, The Edge of Escape. Let us return briefly to Sagittarius A, our black hole, the 1/4 million solar masses in weight, sitting at the centre of our home galaxy, 26,000 light-years from the star system you inhabit, the nearest supermassive black hole, the one whose properties we can measure with the greatest precision, whose environment we can study with the finest resolution, whose behaviour provides our most direct observational access to the physics of these objects. There is a star orbiting Sagittarius A that deserves extended attention, because it is one of the most extraordinary objects in contemporary astrophysics, not for its intrinsic properties, which are those of an ordinary massive star, but for what its motion reveals. The star is called S2. It belongs to a cohort of stars known as the S cluster, a group of massive blue stars with orbits so tight around the galactic centre that they pass within a fraction of a light-year of the event horizon of Sagittarius A. These stars are not ancient. They are young, massive and blue, suggesting they formed within the last few tens of millions of years, which raises a profound question. How did young stars form in the tidal environment immediately surrounding a supermassive black hole, where the gravitational forces should be strong enough to prevent the collapse of gas clouds into stellar nurseries? This is called the paradox of youth, and it remains partially unresolved. S2 completes one full orbit around Sagittarius A in approximately 16 years. Its orbital period is 16 years. For comparison, Earth takes 1 year to orbit the Sun. This star, containing more than 14 times the mass of our Sun, orbiting a black hole 4 million times the Sun's mass, completes that orbit in 16 years. At the closest point of its approach, periapsis, S2 passes within approximately 120 astronomical units of the event horizon of Sagittarius A, screaming past at nearly 3% of the speed of light. 3% of the speed of light is approximately 9,000 kilometers per second, not per hour, per second. In 1 second, S2 at periapsis covers 9,000 kilometers, roughly the diameter of Earth, and then covers it again and again and again continuously, for the months during which it is near the closest point of its orbit. We have observed S2 complete a full orbit. We began tracking it and the other S-cluster stars in the 1990s, using adaptive optics on large ground-based telescopes, technology that corrects for the blurring effects of Earth's atmosphere, allowing diffraction-limited imaging, and then with the gravity instrument at the Very Large Telescope Interferometer in Chile, which combines the light from 4 large telescopes into a single virtual instrument of extraordinary resolving power. In 2018, S2 reached periapsis, its closest approach to Sagittarius A, and the gravity instrument measured its motion with sufficient precision to test specific predictions of general relativity. The results confirmed, with exquisite precision, that the motion of this star matches exactly what general relativity predicts for an orbit around a 4 million solar mass compact object. Specifically, they confirmed gravitational redshift, the light from S2, climbing out of the gravitational potential well of Sagittarius A, losing energy, and shifting toward longer wavelengths, exactly as Einstein predicted in 1915. And they confirmed relativistic precession. The orbit of S2 does not close into a perfect ellipse that repeats identically on every pass, but instead rotates slightly, the long axis of the ellipse turning by a measurable angle with each orbit, tracing a rosette pattern through space over decades of observation, exactly as general relativity demands. These are not indirect or approximate confirmations. The precision of these measurements, the degree to which the data matches general relativistic predictions and excludes alternative theories, represent some of the most stringent tests of general relativity ever performed, not in the controlled environment of a laboratory or a particle accelerator, but in the actual extreme gravitational field of a real supermassive black hole. The universe is running a continuous physics experiment with our nearest supermassive black hole, and the experiment, every single time the results arrive, says the same thing. Einstein is still correct. This is extraordinary. It is one of the most profound facts in the history of science that a theory developed by a single human mind in 1915, without the benefit of computers or particle accelerators or space telescopes or any of the technological apparatus of modern physics, continues to pass every test we devise for it, including tests conducted in the most extreme gravitational environments in the observable universe. It is also, in a specific way, ominous. Because if the theory is correct to S2's scale, and it is demonstrably and precisely, then we know what happens to everything that crosses the event horizon of Sagittarius A. We know the geometry of spacetime inside it. We know that the geometry leads, without deviation, without exception, without any possible escape route, to the singularity, the place where the theory itself stops working, where general relativity reaches its own boundary and produces infinities that tell us it is no longer valid. 26,000 light-years away, at the center of our home galaxy, there is a boundary where physics stops, and it has been there patiently, precisely since before the Sun existed. Act 8. Gravitational waves and the sound of merger. For all of human history, astronomy was built from a single sense: light. Electromagnetic radiation in its many forms, visible light, infrared, ultraviolet, radio, X-ray, gamma ray, was the only carrier of cosmic information available to us. Our entire picture of the universe, every galaxy, every nebula, every quasar, every black hole candidate, every stellar population, every cosmological structure, was assembled from photons, from electromagnetic waves arriving at our instruments after journeys measured in years and thousands and millions and billions of light years. It was an extraordinary achievement. Everything we knew about the universe, everything we thought we understood about its structure and history and contents, was built from one kind of signal. But it was also a limitation, because the universe generates information in other forms, information that electromagnetic radiation cannot carry. Information encoded in a different medium entirely, in the geometry of spacetime itself. Then on September 14, 2015, at 5:51 in the morning Eastern Time, that limitation ended. The LIGO gravitational wave detectors, 2 L-shaped interferometers with 4-kilometer-long arms, one located at the Hanford site in Washington state and one in Livingston, Louisiana, simultaneously record a disturbance that had been expected theoretically for decades but never before detected. A chirp, a transient signal lasting approximately 0.2 seconds, sweeping upward in frequency from 35 to 150 Hz, corresponding to a change in the length of each detector arm of approximately 1,000th the diameter of a proton. A proton is approximately 10 to the power of -15 meters across. 1,000th of that is 10 to the power of -18 meters. The LIGO detectors measure displacements smaller than that. They measure, with laser interferometry, a length change so small that it makes the atom look macroscopic. They measure the spacetime distortion produced by a gravitational wave, a ripple in the fabric of the universe, with an instrument whose fundamental noise sources include the quantum uncertainty of photon position and the thermal vibration of mirror atoms, and which requires isolation from seismic noise, acoustic noise, and gravitational gradient noise to a degree that represents one of the most extraordinary engineering achievements in human history. Two black holes had merged 1.3 billion light-years away. The signal that reached our detectors on that September morning had been traveling across the universe for 1.3 billion years, since an era when the first complex multicellular life was only beginning to emerge on Earth. And when it passed through our planet, it briefly and infinitesimally compressed and expanded the distance between the test masses in the LIGO detectors by an amount that we measured. And in measuring it, we opened a new window on the universe. The detection of gravitational waves from merging black holes, formally announced by the LIGO Scientific Collaboration and Virgo Collaboration on February 11, 2016, and recognized with the Nobel Prize in Physics into 2017, inaugurated what astronomers call the era of multi-messenger astronomy. For the first time, we were not merely observing the universe with light, we were hearing it, detecting the gravitational screams of colliding black holes with an instrument whose sensitivity to displacement rivals the quantum limit, whose reach extends across billions of light-years, whose data stream represents a completely new class of information about the most violent events in the cosmos. Since that first detection, designated GW15914, the LIGO and Virgo detectors and their Japanese counterpart Kagura have recorded dozens of black hole merger events. Each one is a signal from a catastrophe incomparably more violent than anything else in the universe. Two black holes, each containing tens of solar masses, spiraling together at a significant fraction of the speed of light, merging in a fraction of a second, briefly converting several solar masses worth of rest mass energy directly into gravitational wave radiation. Each detection is a direct observation of gravity itself, the weakest of the four fundamental forces, operating in its most extreme regime. But all of these detections have been of stellar mass and intermediate mass black holes, compact remnants of stellar evolution, up to a few hundred solar masses at most. The gravitational wave frequencies produced by these mergers fall in the range of tens to hundreds of hertz, the LIGO band. The gravitational waves produced by supermassive black hole mergers, by the eventual coalescence of Sagittarius A and Andromeda's central black hole, for example, or by the merger of any of the pairs of supermassive black holes currently in slow orbital death spirals across the universe, oscillate at nanohertz frequencies, periods of years completely outside the LIGO band, completely undetectable by ground-based interferometers. Detecting them requires an entirely different instrument, an instrument at a completely different scale, a galaxy-sized instrument. This is the operating principle of pulsar timing arrays. Millisecond pulsars, neutron stars spinning hundreds of times per second, with the regularity of atomic clocks, emitting radio pulses with a precision that rivals the best human-made time standards, are distributed throughout the Milky Way at distances of thousands of light-years. If a gravitational wave passes through the galaxy, it should produce a correlated pattern of timing residuals across the array, all pulsars showing anomalies simultaneously. The anomalies correlated in a specific pattern predict by the angular distribution of gravitational waves on the sky, a pattern called the Helings-Downs correlation after the two physicists who derived it. In 2023, the announcement came from multiple independent collaborations simultaneously. Nanograv in North America, the European Pulsar Timing Array, the Indian, Chinese, and Australian collaborations. All of them analyzing years of pulsar timing data with different instruments, different data reduction pipelines, different analysis methods. All of them finding the same thing: evidence for a gravitational wave background. A constant pervasive low-frequency hum of gravitational waves permeating the entire observable universe. Not a single source. A background, a superposition of gravitational wave signals from an enormous number of separate sources, blending together into a continuous stochastic background, the way the noise of a city blends into a constant roar. The Helings-Downs correlation was present in the data, matching predictions to a high degree of statistical significance. The most probable source, supermassive black hole binaries. Pairs of supermassive black holes scattered across the universe, in the cores of galaxies that have merged, circling each other on orbits that decay over millions and billions of years as they radiate gravitational energy away. Hundreds of millions of such pairs, perhaps, each emitting gravitational waves at nanohertz frequencies, their combined emission producing the background that pulsar timing arrays have now detected. The universe is filled with these systems, sleeping giants paired in slow-motion orbital death spirals. Their gravitational wave emission washing through everything, through galaxy clusters, through interstellar space, through the atmosphere of the Earth, through the walls of the buildings you live in, through the atoms of your body. Right now, at this moment, as you read these words, the universe is vibrating. We are only now beginning to feel it. Act 9. What happens at the edge? There is a concept in general relativity called the photon sphere, a region of extreme space-time curvature around a black hole where the gravity is so intense that light itself follows circular orbits. At a radius of 1.5 times the Schwarzschild radius, halfway between the event horizon and twice its distance from the center, photons traveling perpendicular to the radial direction are in circular orbits. They race around the black hole at the speed of light, following a path that curves back on itself due to the curvature of the surrounding spacetime. The photon sphere is unstable. A photon at exactly this radius will orbit, but any slight perturbation, a tiny fluctuation in its trajectory, a fractional deviation from the perfect circular path, will send it either spiraling inward toward the event horizon or outward to escape. It cannot remain in the circular orbit indefinitely. But at any given moment, photons that happen to be following circular trajectories at the photon sphere radius, photons that have been captured into these brief circular passages, are racing around the black hole at the speed of light, complete into circular journeys of tens or hundreds or thousands of millions of kilometers. Some of them have orbited multiple times, looping around again and again before a perturbation finally deflects them outward. When you look at the image of M87 produced by the Event Horizon Telescope, that orange ring of light around a region of shadow, you are not looking at the event horizon. The event horizon is inside the image, inside the shadow region, invisible because no light escapes from within it. The orange ring is not the boundary of the black hole. It is the accumulated glow of light that has circled the black hole 1, 2, 3 times. Photons from the hot accretion disk and surrounding environment that were bent into near-circular orbits by the extreme spacetime curvature, looped around the black hole, and then escaped outward to eventually reach our telescope after traveling 55 million light-years. That orange ring is the photon ring, the accumulated trajectory of light that traveled in circles around a 6.5 billion solar mass object, light that completed circular journeys of billions of kilometers before escaping. Think about the image differently now. It is not a photograph of a black hole in the sense that an ordinary photograph captures what something looks like from the outside. It is a photograph of the behavior of light in the most extreme gravitational field in the observable nearby universe. A record of spacetime curvature so extreme that light itself lost its straight-line trajectory. A portrait of gravity at its most absolute. And if you were to fall in, if, hypothetically, you were to approach the event horizon of a large, supermassive black hole, one with an event horizon large enough and a tidal force at the boundary, gentle enough that you were not immediately spaghettified, not immediately stretched into a thread of plasma by differential gravity, what would you experience? Here is the answer that makes physicists uncomfortable to give in public, because it is correct and it is deeply strange, and it challenges a deeply held intuition about what a boundary as consequential as the event horizon should feel like to cross. You would not notice crossing the event horizon, not at the moment of crossing, not by any local physical measurement. The equivalence principle of general relativity, one of the foundational principles from which the entire theory was constructed, states that a freely falling observer in a gravitational field is locally indistinguishable from an observer floating in free space, far from any gravitational source. The same principle that explains why astronauts feel weightless aboard the International Space Station. They are in free fall, and free fall locally feels like the absence of gravity, applies to free fall toward a black hole. At the moment of crossing the event horizon of a sufficiently large, supermassive black hole, there is no local physical measurement, no instrument reading, no bodily sensation, no observable deviation from the physics of free space that would alert you to the fact that you had just crossed the most consequential threshold in the observable universe. The spacetime curvature at the event horizon of M87 or TON 618 or Phoenix A is actually modest by the standards of extreme gravitational environments. The tidal forces at the horizon are gentle enough that you would not be disrupted. Your atoms would hold together. Your instruments would function normally. You would feel nothing unusual, but you would be inside. And inside, the geometry of space-time has a property that is so foreign to everyday intuition that no analogy fully captures it. Inside the event horizon, the radial direction, the spatial direction pointing toward the center, toward the singularity, acquires a fundamentally different character. In ordinary space-time, the radial direction is spatial. You can move toward the center or away from it. You can choose. You can stop. In ordinary space-time, you can hover at a fixed radial distance from an object with sufficient thrust. The singularity is a place in space, and places in space can be avoided. Inside the event horizon, the radial direction becomes time-like. It acquires the same mathematical character as the time direction. And time, unlike space, flows in direction only. Time cannot be reversed. You cannot travel backward in time. The future is not a place you can choose to avoid. It is a direction in space-time that everything that exists moves along, continuously and without exception. Inside the event horizon, the singularity is not a place in your future spatial environment. The way the surface of a planet would be a place you could steer away from. It is your future. It has the same relationship to your present moment that next Tuesday has to today. Not a spatial location you could turn away from, but a temporal inevitability you cannot avoid by any means. The singularity is your future. Every world line inside the event horizon, every path through space-time available to any observer, any particle, any photon, leads to the singularity at some finite proper time. For M87, the time between crossing the event horizon and reaching the singularity is approximately 14 hours. For a smaller stellar black hole, it might be measured in microseconds. For TON 618, with its 66 billion solar mass singularity and its event horizon 26 solar systems wide, the time might extend to several days. You would have time to think, time to observe the interior of the black hole, time to make measurements in a region of the universe from which no information will ever escape. A private laboratory sealed permanently from the rest of the cosmos. Whatever you observed in those final hours, whatever physics operated inside the event horizon, whatever the space-time geometry looked like as the singularity approached, whatever the quantum structure of the black hole interior revealed, would remain sealed there forever, inaccessible to any observation from outside, contributing nothing to the stock of human knowledge. The black hole keeps secrets, perfect mathematical absolute secrets. Whatever you learned inside would die inside, and the universe outside would never know what you found. Act 10, the universe's final architects pull back now. Pull back from the singularities and the event horizons and the photon spheres and the infalling trajectories and the private physics experiments conducted in sealed gravitational chambers. Pull back to the scale of the observable universe, a sphere approximately 93 billion light-years in diameter, containing an estimated 2 trillion galaxies, each galaxy containing on average hundreds of billions of stars, each major galaxy containing a supermassive black hole ranging from a few million to hundreds of billions of solar masses. 2 trillion supermassive black holes, 2 trillion gravitational engines, each containing the compressed equivalent of millions to billions of suns, each sitting at the center of a galaxy it helped build and continues to regulate, each connected to the surrounding cosmic structure through its gravitational influence, its jet activity, its feedback on star formation, and its contribution to the gravitational wave background that now permeates the entire universe. This is not a peripheral feature of the cosmos. This is not a population of exotic objects occupying extreme corners of the universe, while the main story of stars and galaxies proceeds independently. The supermassive black holes are in the main story. They are the main story. The cosmic web, the extraordinary large-scale structure of the universe, the filaments and sheets and nodes and voids that give the universe its texture at the very largest scales, was not built by ordinary matter under ordinary gravity alone. It was built in part, shaped decisively, by the feedback of 2 trillion galactic center engines over 13 billion years of cosmic history, by the jets that punch through galaxy clusters and inflated cavities that persist for billions of years, by the radiation winds that swept gas out of galaxies and prevented the formation of stars that would otherwise have formed, by the gravitational influence of billion solar mass objects on the orbital dynamics of everything around them, by the gravitational waves emitted by pairs of supermassive black holes spiraling toward merger, waves that carry energy out of these systems and deposit it in the surrounding space-time. The universe does not have black holes in it the way a room has furniture in it, occupying space without fundamentally altering the room's character. The universe is, in a structural sense, built around its black holes. They are the load-bearing walls. Remove them from the history of the cosmos, and the universe that results does not resemble ours, and it is not finished. Across the universe, supermassive black holes continue to grow, to feed, to eject jets. Some galaxies are currently in active phases, quasars blazing with the power of billions of suns, their jets carving cavities in the hot intracluster medium that are visible in X-ray images as dark holes in the thermal emission of the gas, like bubbles blown through thick liquid. These cavities, some of them larger in volume than the Milky Way galaxy, are the architectural fingerprints of black hole activity. Ghost structures, imprinted on the largest gravitationally bound objects in the universe by the energy released in a region smaller than the solar system. The black hole leaves its mark on everything. The black hole has always left its mark on everything. And when the universe reaches its far future, when the last red dwarf stars have exhausted their hydrogen fuel over timescales of trillions of years and the last stellar populations have faded, when the galaxies have dispersed their constituent stars through gravitational interactions over quadrillions of years, when the light of ordinary astrophysical processes has faded to nothing, and the universe has entered the long dark era that cosmologists call the black hole era. The supermassive black holes will still be there, not fading, not quiet, dominant. The last significant structures in a universe that has otherwise gone dark. The last gravitational anchors. The final repositories of organized matter and information in a universe that has thermalized everything else into a cold, diffuse, featureless void. Slowly, over timescales measured in googles of years, Hawking radiation will reduce them. The last activity in the universe will be the faint, incredibly cold thermal glow of these dying giants, brightening infinitesimally as their mass decreases, and the temperature of their radiation increases, until, in final bursts of gamma rays that will propagate outward through an otherwise completely dark and empty universe, the last black holes evaporate. The last light in the universe will be black holes dying. They were among the first things to form, perhaps before the first stars. They will be the last things to fade, long after the last star has cooled to darkness. The supermassive black holes were not here for us. We were here, briefly, because of them. Act 11. The question we cannot answer here, at the edge of everything we know, there is a question that sits beneath all of the physics, and all of the observations, and all of the extraordinary facts that have filled this descent. A question not about mechanism, not about how black holes form or grow or feed or eventually evaporate. Those questions, difficult as they are questions of detail, questions that ask for the next layer of specification in a picture whose broad outlines are established. The question I mean is of a different character. Why does the universe produce supermassive black holes at all? Not in the mechanistic sense, not the sequence of physical processes that produce them, but the deeper question. Why is the universe structured such that every large galaxy requires one? Why is the correlation between black hole mass and stellar bulge mass tight to within a factor of a few across all galaxy types, all cosmic epochs, all environments, across the full 13 billion year history of cosmic evolution? Why does the universe appear to be calibrated such that the formation of galaxies and the formation of their central black holes are connected through a feedback loop of extraordinary precision and universality? The tight correlation was not predicted by any theory developed before it was observed. It emerged from the data, unexplained, demanding explanation. Every subsequent theoretical attempt to explain it has reproduced the correlation to some approximation, but the true mechanism, the specific physics that makes the ratio of black hole mass to bulge mass so consistent, so universal, so independent of the particular history of any individual galaxy, remains a matter of active debate. And the deeper question underneath the mechanistic one has not really been asked in the framework of mainstream cosmology, because it sounds uncomfortably like a question about purpose, and physics does not deal in purpose. But it can be asked without invoking purpose. It can be asked as a structural question about the laws of physics themselves. Why do the laws of physics, as written, naturally produce gravitational regulators at the centers of galaxies? Why does a universe governed by general relativity, quantum mechanics, and the standard model of particle physics, without any additional ingredients specifically designed to produce this outcome, naturally evolve toward a structure in which the most destructive gravitational objects in existence regulate the most constructive astrophysical process, star formation, with a precision that produces the observed universe? The physicist Eugene Wigner wrote about the unreasonable effectiveness of mathematics in describing the natural world. The mysterious fact that mathematical structures developed for their internal logical elegance turn out to match physical reality with extraordinary fidelity. The correlation between black holes and galaxies feels like a specific, unsettling instance of this mystery. The universe has calibrated its most extreme objects to its most fundamental structures, with a precision that does not feel like coincidence. It feels like the universe is doing something systematic, something that the equations demand, without our having fully understood why the equations demand it. It feels like the universe is doing something, we do not know what, and that uncertainty, that specific fundamental physics-level uncertainty, is perhaps more unsettling than any of the facts about event horizons and singularities and information paradoxes that preceded it, because a fact about an event horizon is a fact about a specific extreme place. Unsettling, certainly. Contained. The uncertainty about why supermassive black holes exist and why they are what they are is an uncertainty about the laws of the universe itself, about why the rules are written the way they are, about whether we have yet understood anything more than the surface of what the universe is actually doing. We may not have. Act 12, the last light, we began this journey with an invitation. Imagine standing at the center of our galaxy. Now at the end, having descended through the physics and the paradoxes and the observations and the questions that have no answers yet, a different invitation is appropriate. Brooder, longer in time, more final, imagine the last day. Not the last day of the Earth, that will come in approximately 5 billion years, when the Sun completes its main sequence evolution and begins expanding into a red giant, swelling outward past the orbit of Mercury, past Venus, past Earth, consuming them, or at minimum sterilizing them, ending the biography of this world as definitively as a period ends a sentence. A natural death. The ordinary fate of a water-bearing planet orbiting a sun-like star, played out over timescales that reduce human history to an epilogue. Not the last day of the Sun, which will itself end as a white dwarf, a cooling ember of electron-degenerate carbon and oxygen, slowly radiating its remaining thermal energy into the surrounding cosmos over trillions of years, fading from white Oslo to orange to red to the permanent infrared glow of a black dwarf in a universe that will have moved far beyond caring about it. Not the last day of the Milky Way as a distinct structure, which will have merged with Andromeda 4.5 billion years from now, the two spiral galaxies slowly combining into a new, larger elliptical galaxy, their star distributed onto new orbits, their gas consumed in the bursts of star formation triggered by the collision, their central black holes spiraling toward each other on a timeline of tens to hundreds of millions of years after the galactic merger begins, finally coalescing into a single larger black hole presiding over the galaxy that results. Imagine the last day of the black holes themselves. The black hole era is what cosmologists call the period of the universe's far future that begins after the last stars have burned out, a period beginning roughly 10 to the power of 40 years from now, after which the universe is populated by the dead remnants of stellar populations. White dwarfs cooling toward black dwarfs over incomprehensible timescales, neutron stars spinning down as they radiate rotational energy through magnetic dipole emission, the occasional small stellar black hole, the large-scale structure that shaped our observable universe, the filaments and sheets and nodes of the cosmic web, the galaxy clusters and superclusters that represent the largest gravitationally bound structures, has dissolved. The continued expansion of the universe having driven everything apart to distances so vast that even gravity between the largest structures has become negligible. The universe is cold, dark, quiet, not the temporary quiet of a calm, the permanent quiet of thermodynamic desolation. The heat death is not yet complete, but it is visible from here. Only the supermassive black holes remain as structures of any significance. Isolated, vastly separated from each other by the expansion of the universe, slowly growing by capturing the last scattered particles that drift across their event horizons in the emptying cosmos. The universe around them is not merely dark. It is a void in a sense that the word void cannot adequately communicate. Not the vacuum of interstellar space which is populated with atoms and photons and cosmic rays and magnetic fields and neutrinos. A void more complete than that. A void in which the mean free path between particles is measured not in light years but in units billions of orders of magnitude larger. A void in which the cosmic microwave background has been stretched by the expansion of the universe to wavelengths longer than the observable universe itself. There are no photons of visible light anywhere. There are essentially no photons of any wavelength. There is essentially nothing. But the black holes are there, and Hawking radiation, the faint quantum glow at the event horizon, the slow thermal leak that returns mass to the universe one virtual particle at a time, is still operating. It has always been operating. The rate of mass loss is so extraordinarily small that in the current universe it is swamped by accretion from the surrounding environment. But in this future universe there is no surrounding environment. There is nothing to accrete. And so, over timescales that begin at 10 to the power of 90 years and extend to 10 to the power of 100 years. Numbers that do not fit within ordinary human comprehension. Numbers that are not smaller than the age of the universe, but are larger by more than you can think. The great black holes begin, grain by grain, quantum by quantum, to lose mass. The process accelerates as the mass decreases. As a black hole loses mass, its Schwarzschild radius shrinks. As its radius shrinks, the spacetime curvature at the horizon increases. As the curvature increases, the temperature of the Hawking radiation increases. As the temperature increases, the rate of mass loss accelerates. A black hole in the final stages of evaporation is not cold and faint. It is hot and bright, briefly, for the last instance of its existence, radiating gamma rays at temperatures that would not be out of place on the surface of a neutron star. The final evaporation, the last tiny fraction of the original mass being converted to a brief burst of high-energy radiation, is the last energetic event in the universe. The last transmission, the last light, and then there is nothing, no more black holes, no more organized structures of any kind, no more stars, no planets, no atoms in chemical bonds, no temperature gradients of any significance, no information processing of any kind. Just the expanding quantum vacuum, cooling toward its absolute thermodynamic ground state, in a universe that has completed the full cycle of its biography. From the hot, violent, information-dense chaos of the early universe, through the long middle period of star formation and galactic evolution, and the brief local experiments in chemistry and biology and consciousness that some of those processes permitted, to the cold, quiet, featureless, maximally entropic endpoint. The supermassive black holes were not monsters in this story. They were something stranger than monsters, something more essential. They were the frame, the load-bearing architecture without which the picture could not have been painted, the engines that built the galaxies, the regulators that controlled star formation, the gravitational anchors that organized the cosmic web, the last structures standing in the long dark of the universe's old age, and the last light in the universe's final silence. They were here before almost everything. They will be here after everything else is gone. And here you are, 26,000 light-years from the nearest one, on the third planet of an unremarkable yellow star in the outer third of a spiral arm of a moderately sized barred spiral galaxy, protected by distance, by the cold vacuum of 26,000 light-years of interstellar space, by the simple fact of your existence at this particular coordinate in the universe and not somewhere closer to the center. The universe did not design itself to accommodate you. The physical laws that govern every process from quantum fluctuations to galactic dynamics were not written to produce your existence as an outcome. They were written, if written is even the right conceptual frame for what physical laws are, around a different priority. Around gravity, around the collapse of matter, around the formation of the compact objects that gravity, given sufficient mass and time, inevitably produces. The supermassive black holes were always the priority. You exist in the margin, in the comfortable, starlit, moderately scaled region of a galaxy whose center is 26,000 light-years away, where the gravitational drama of Sagittarius A is an abstraction so remote that you have never felt it, will never feel it, will live and die without the event horizon of your galaxy's central black hole having any direct physical effect on you whatsoever. You exist in the spaces between, in the quiet interval between the anchor points, in the accidental corner of the universe's architecture where the feedback and the jets and the tidal disruption events are someone else's problem, for now, but the quiet is not guaranteed. The Milky Way is 100,000 light-years across, but it is rotating. Stars migrate, orbits precess. The galactic center is always there, always waiting, patient in the way that only a 4 million solar mass gravitational singularity can be patient, which is to say, with perfect absolute mathematical indifference to whether you exist or not, whether you are afraid or not, whether you understand it or not. Sagittarius A has not had a major feeding event in approximately 4 million years. It will have one again. It does not know this. It does not anticipate. It simply exists, curving spacetime around itself in the geometry that general relativity prescribes, accumulating mass from anything that crosses the threshold, operating according to physical laws that have not changed since before the Earth formed, and will not change after the last star the universe will ever produce has cooled to nothing. The universe keeps building things. The black hole keeps the receipts. Everything that crosses the event horizon stays. Everything that has ever fallen in is still there, sealed in the singularity's eternal accounting, locked away beyond the boundary where physics ends and whatever replaces physics begins. The universe's most permanent record keeper, the most efficient destroyer, the architect and the abyss. 4 million solar masses of curved space-time, sitting at the center of the galaxy that contains your star, patient as mathematics, final as physics, permanent as the laws that produced it and cannot fully explain what is inside it. 26,000 light-years away. Tonight, when you look toward the south, toward Sagittarius, that dense star field low on the horizon that marks the direction of the galactic center, you are looking approximately toward it, not at it. The black hole emits nothing visible at this distance. The event horizon emits no light that escapes from it. The accretion disk is currently too dim to see at 26,000 light-years with the naked eye. There is nothing to see in the direction of Sagittarius A, no glow. No darkness distinguishable from the surrounding darkness, but it is there. The stars in the direction of Sagittarius are real. You can see their light, but what you cannot see, hidden behind the dense clouds of gas and dust that obscure the galactic center in visible wavelengths, is the monster at the middle of everything. 4 million times the mass of the sun, the boundary where physics stops, the silence at the center of the galaxy. It was here long before you arrived. It will be here long after you are gone. It will be here, patient and absolute and indifferent, long after the sun has died, and the Earth has been consumed, and the Milky Way has merged with Andromeda, and the merged galaxy's stars have dispersed into the void, and even the white dwarf remnant of the sun has cooled below any temperature that the word warm could apply to. It will be the last significant structure in what was once the Milky Way. And then, grain by grain, in Hawking radiation too cold to detect by any instrument that could conceivably exist, over timescales that make the age of the universe look like a brief morning, it will give back what gravity took. And then it too will be gone, and there will be nothing, no more architecture, no more abyss, no more frame for a picture that no longer exists. The cosmos, this vast, cold, extraordinary, indifferent engine of physics, did not build itself for us. It built itself around them. We are the accident. They are the architecture. And the architecture will stand in patient, gravitational silence, long after the last word any human being will ever speak has been spoken, and the last thought any human mind will ever think has faded, in permanent and absolute and beautiful dark. There is no edge to fall off of out here. There is only the event horizon. And beyond the event horizon, there is only the singularity. And the singularity is where the questions end. And some of them, in the end, were never meant to have answers we could hold. If this descent into the architecture of everything left you looking at the night sky differently, if it planted something in you that will not leave easily, a question or a dread or a specific kind of wonder that has no comfortable name, then share this. Not because the algorithm rewards it, though it does, but because the universe does not announce itself. It waits for someone to look. And the more of us who look, the closer we get to the answers hiding at the edge of physics, at the center of everything, in the sealed silence beyond the event horizon. The black hole is waiting, so is the truth. And unlike you, neither of them is in any hurry.